the game actually got to name them. Big Bute is a Highland cleric that we found in the game. It's a good name. And, the fact that he has 69 hit points is a coincidence, but it's still a pretty funny coincidence. We've entered the code. Because of your superior intellect and diligence, you have saved Kron and all of its warrants. This ship, created by the ancients, is a grand experiment designed to populate this distant world. Prepare to beam down in Might and Magic 3. It's here, on the floor. I didn't see it. Thank you, my friends. You have banished chaos and rejected the false path of uncompromising order. Under the weight of the evidence and from the skilled pressure tactics of your lawyer, Lucas breaks down and admits to their crime. Congratulations, Ace. I think we're having a real moment here. I've changed my mind. I can't give her up. You can have your money back. How could I sell something so dear? Then again, a deal's a deal, right? Right? Catch you later. Good luck. Enjoy. I'm out of here. Let's pick up the bottle of grog here. Pick up the root beer. Use the root beer with the jug. Apparently root beer works very well. We get to see an instant replay. And a view from the blimp as well. I wonder what would happen if I tore the leg off this thing. Ark.
You have a resume. Madre de Dios, es el cuello diablo. Come on, I'm ready for you.
Yeah. Here it goes.
Enter visualization request.
Let's try it in the other order.
Circuit code accepted. 64523 1 recognized. Beginning message.
Grand experiment of the ancients to use the technology of elemental manipulation to create a completely viable ecological and social microcosm. This microcosm was then to be transported to a distant biosphere, Terra, to supplant its indigenous ecosystem. The need was acknowledged for a central controlling unit capable of compensating for expected anomalies.
Well struck. That looks like a fatal blow.
Yeah, die.
My death will not save you from our wrath.
Are you going to plug me into Link, sir? I hope you know what you're doing.
I have no idea what we're doing. And
Something is happening, I think. Yes, I'm gaining control. I found my destiny, Mr. Foster.
goals in the middle. Perhaps we didn't even need to know that. The yellow crystal is over on the left side. And the blue one is on the right side. Switch to Annie. Have her pull the lever to close the trapdoor. Have her push the switch on this side. Switch to Zack. Have him push the switch on this side. On our way through this wall. Another mini boss. Welcome in, guys. Hope you're doing okay. Been a while since we did one of those development streams. Hope you can actually hear me. Just getting everything set up here. There's some trickery pokery that I need to do here. A little bit at least. One of them is using a small program called Auto Hotkey to change the window title of the emulator so that the 80 column window and the 40 column window are don't both have the same title. That doesn't work very well. So let me get that over and done with. If I can't find the script that I made last time to do this. Let's see. Let's see. I can easily just make another one. Not terribly complicated. So please save it right here in the same location. This is a shortcut to where? Okay. Here's the script. Well, does it rename one of the windows so it has a different name? Because that's definitely a problem with the OBS capture. You need to give it a window name to capture, and if both of the windows have the same name, it's a problem. It doesn't really matter which one it names what. It's just important that they don't have same name. So let me just, this is supposed to be the 80 column window, and I can easily fix this. So it's supposed to be capturing this, and the 40 column one is supposed to be capturing this. That's the 40 column one. That's the 80 column one. Let me fire up Ultra Edit. See the editor. You should be able to. Might have changed the name of the. Let me see what's actually there. There it is. Okay. Just to rescale this a little bit. Can be quite a bit wider than it is. There we are. That's roughly it. Okay. I can see this. We can see this. I need to. Things I need to do here is. Set this. Like this. And I need to fire this up. Let's get some. Fire up background music as well. That's nice. No, the game is not ready. Not at all, but not at all. I've spent some time on it, but I haven't had that much time to spend on it. It's actually been a while since I was even able to do a stream of this. My wife has been working very hard on a project at work, and she's been very busy many nights, so I've been some limits as to how much time I've been able to stream. Let's see. Let's go over where we are roughly. We fire up the 40 column mode here. think I already have the latest build running on the Windows machine, but just in case I'm going to run the build script. Chip 8? What's chip 8? Is that a system or? Switch to 80 color mode to play game. Right. It has music now. What I have discovered though is that the capture butchers the music, the SID, the noise canceller on the I have a noise canceller on the mixer because there tends to be a little bit of added noise. It's a bit interesting. Let me see if I can't make it output to at least. Okay, now it works. You can hear a vast difference in the sound quality. I don't think we've even seen the game for a long time. We one point had this little maze setup which we drew in the map editor. I don't remember if you I might have shown it to you at some point. Let me refresh our memory of that a little bit. We know what we're actually looking at. I have it here somewhere. If I don't, I can easily fire it up. How do you like my SID? I've never made a SID before. It's my first attempt. Kinda sucks, but it's not terrible. I made a few tunes. This is basically the main one, and I have a couple of sub tunes as well. Early fantasy computer console, simple as simple. Fun. Limitations are quite fun with this. So, programming when you have all the resources in the world is one thing. Programming on a system like this is a totally different thing. capture it even. Yeah, there it is. That's the map maker. That's roughly the map we're looking at. Using the map maker isn't particularly complicated. You just click on whichever square it is that you want to edit. Then you can basically select whether it's empty, solid, a door, or a fake wall. Then you can save it out in a .dat file, which is then included in the build script to actually incorporate it into the game. Makes 4 separate arrays depending on which direction the user is looking at to make the turn code simpler to program. That's basically what we're looking at. And if we position ourselves back in what's displayed on the 40 column, this is basically just a debug. It shows exactly the values of the array for both the square directly north, west and east, and then 2 squares to the west and 2 squares to the east, and so on. And so I have it running on the 40 column screen so I can use it for debug purposes. It took me a while to finish the drawing code, but other than adding the SID support, I haven't really done much else. The SID support is just a simple player that's running in the background. So to refresh, we're basically, if we take a look at this, we're basically here. This is what we're looking at. We're positioned here. We're looking at this particular wall. The game still doesn't show any difference between a door and a solid wall and so on. It's just it's all the same. I haven't added any graphics for the doors and so on, but it's largely, it's not terribly complicated. That's obviously one thing we need to do, but it's not perhaps a requirement to move on. So we can now turn in all directions. I've set the game up in a way that you can either use the numeric keypad, so you can use 4 to turn right once, twice, 3 times, 4 times. Now we're facing back the same direction. There's no compass anywhere. Although that would really be very easy to add, since the game knows perfectly well which direction you're oriented. Or you can obviously turn left as well. That's the same, you end up in the same circle. Then you can, using the numeric keypad 6, or you can use the cursors as well. The cursors are very useful for the emulator, because the numeric keypad is more useful for the actual Z128, because the cursor keys on the 128 are a little bit annoying, as they are on the 64 as well. But if you're doing this on an emulator, it's very nice to be able to use the arrow keys as well. And then of course you can move forwards and backwards. The same applies with the arrow keys. So we can we go here and then we turn left and walk 1 forward. We can look at what it looks like. We're facing this. Now there are limits as to how far I draw. I only draw basically 4 squares forward at the very max. So you can't always see everything moving forward. That's just to simplify the drawing code and also to reduce the processing load. So once we move forward, you can now see this wall, which we didn't see here. And, that's not really a bug. It's just somewhat the way I want it to be. Because at some point we need to draw the line somewhere. So we can go here, and of course we can go 1 step closer. And of course we can turn around and look closely at the walls. And the drawing code is largely complete. I don't think there's any serious issue left in it. There are occasional glitches like this. You can't see the tiny wall that maybe should be here, but I'm not going to I'm not going to worry about these itty-gritty details. And it's a maze runner at the moment, and you can just go around, and it's decently fast actually. You can it's perfectly reasonably fast. It's not glitchy at all. There's a little bit of blinking because it does need to redraw and do all sorts of things, and there is no double buffering. But it's not bad. It's better than really what I thought it would be. Of course, we can go inside as well, just to refresh our memories of what that looks like. It's basically it's like this little maze here with a solid circle in the middle, and this one is a fake wall. There is no current testing for whether anything is solid or not. You could just walk through everything you want. So you can walk through solid walls and do whatever you want, but that check hasn't been done, but that's not really all that complicated either. So you can go around and the idea of the reason why this maze looks like this is because I wanted to stress the drawing code as much as I can, and have as many complicated corners and sides as possible, so I could get this working decently well. Now we're inside the little square in the middle. Of course we can go out again and so on. So this actually works decently well. I'm sure there are bugs in this code, and we'll figure them out as we draw more things and make more complicated maps, but I'm decently happy with it. If we go back to the code itself, let the SID play in the background. Probably best to actually go over how we're using the memory now as well. I think that would be a good idea. We'd already done some work on that before, but it's gotten more complicated. Well, at least slightly more complicated. Okay, it's not, the SID doesn't play on this screen. I guess that's fine. Start the pretzel again. So, the SID was another complication in all of this. As when I started, when I added the SID player, and I stole the SID player from a C64 code base. It's basically just it hacks into the interrupt routine to play the SID on the interrupts, and we'll take a look at it later on. I modified it a little bit so it would work correctly on the 128, which has a different interrupt system than the 64 does. It's slightly more involved, but there's an issue with that, and that issue is that when the interrupts run, the memory management unit of the 128 returns the system to its pretty much default memory configuration, where all the ROMs are in place, and that means that there are limits as to where you can actually place the SID itself. You can't place it anywhere high up in the memory map, because if you do so, the SID is inaccessible when the IRQ routine is being used, because it has a different memory configuration that it did when it leaves. So what happens when the interrupt handler fires, is that it changes the memory management unit register, sets things to a default setting, then it processes all of the interrupts, runs through the code, and before it exits again, it restores it to whatever it was before. So the interrupt handler does all of this automatically for us in the background. What that, however, means is that we can't place the SID somewhere in memory where the interrupt handler can't access it during its run, which means that we're quite limited as to where we can actually place it. On the C64, the SID address is generally at hex 1000. That's generally where that lives. And, most of the SID tunes that you download are placed at this particular hex value. This on the 128, however, is not particularly free. If we go back to the memory map, this is not registered as free, and there's a reason for that. There are some variables in place and other things in place in this memory which are being actively used by the kernel, so you can't really just bank it at 1000 and expect it to work, so that's not actually the case. So what I've done is I've moved it around a little bit, and that means that I needed to move everything around because if you remember, we had the utility module sitting at 1300. So that required us to move that as well. Let me see if I can't. Just copy this here. Yes, I can. And this is basically what it is now. So we have set the utility code start here at 2800 instead, and move that around a bit, and that means we can place the SID at 1300 where the utility code used to be. So what I've done in essence is I've significantly reduced the size of the main down to what is essentially just a few K, and we can easily get away with that because the main code is really just loading all the utilities. It's not really doing much of anything right now. It will contain the main game loop, and it will load all sorts of things and call subroutines from many other things, but the main code isn't all that big to begin with, so the util code will just sit directly after it in memory, and we'll have a little bit of space until we reach the graphic code, which I've reserved the largest room in the block for because it's by far the biggest part. And the assets, the graphical assets and so on, they start at 8000, so we still have plenty of space there. That means we do have a bit of space in memory for the SIDs. They can basically sit from 1300 and up to the 1C00 mark where the basic RAM starts. So we have a bit of space here for the SIDs, but it can't really exceed that size, so the one SID with all the subtunes at the end will have to fit into that space in memory. It easily does that now, and I don't think it will actually be much of an issue. But, that's the basic limitations. You can reuse a lot of things. The code tracker which I'm using to write all of this does offer you the ability to use subtunes, so you can reuse the same instruments and the same wavetables and the same patterns for that matter, using different instruments in the subtunes as you have in the main tunes. The plan for the main game data is that you'll have roughly 16k at least, and then you have something, you have another, and you could bank that as well. So you have 16k and you could bank that to another 16k, so you could have two 16k banks. But there are limits as to what we can actually do. So this part of the memory, which is basically where the assets are from 8000 and up to B88 BFFFF, this is where the asset code is. So this is where we can store the maps and the graphics and so on. And this we can bank. So we obviously have another 64k of RAM we can bank into this space, so we can bank this pretty easily. The code itself that we need to be able to access can't be banked. So this space here from 4000 and up to 7FFF is going to be code. And this space as well from 1C00 and up to 3FFF is going to be code as well. The SID will sit here from 1300 and up to 1C00, so that leaves these 16k that we can bank in and out. Because we need this bank with a kernel ROM and the IO space, which we need to access the VTC. We need this space to be as it is. We can't fiddle around with these 16k, so these 16k are essentially ROM. So part of this is also of course reserved for common registers and so on. So using a decent chunk of it from basically 1300 and up. Then we're using all of this and potentially another bank over here, but this is all ROM. And, even though we have 128k of RAM, there are some limits as to what we can actually do with it. So we can bank around with this one, but we really can't do much of anything else with it. And I'm not sure that's actually going to be a problem, because 16k of free RAM in this particular case, at the moment at least, seems like plenty of RAM. But we'll see. And, if it isn't, we can write some sort of banking code. We could theoretically at least use at least 32k. So we still have plenty of RAM available. We're not running out of space still. We'll see how it turns out. So at least I had to move all of this around a little bit to make the SIDs actually work. And that just means that things end up in a slightly different memory location when it's loaded now. If we go to the if we go back to the development screen. Take a look at the main right now. It's not terribly complicated. Let's see. Just cutting things off here from the. Funny how it's cutting it off from. Zoom in a little bit so you can actually read this. Now, the start of the code is just a sys7181, which just calls the assembly. So this gets placed at the top of basic memory. Means that when you run the code, it will just automatically jump to this address, which will be the start of the main function, which follows directly afterwards. It clears the screen. Then I store a 0 into both the border and screen colors to turn the screen black. Then we load the utility module. and after the utility module has been loaded, we can call the init function, which is part of the utility module. So we'll take a quick look at that right now. The first thing it does is basically set the RAM configuration, and there are individual bits in the RAM control register and the memory management control register that we need to set. And we need to tune basically what's RAM and what's ROM, and whether the IO space is active or not. We can turn off the IO space, but obviously then we couldn't access the 80-column chip. So we start by setting these values here, setting how much memory is shared and how much is bankable. And we place the loading string on the screen, tell the user that we're actually loading the game. It takes 0 time on the emulator, but it will probably take longer on the actual 128. The next thing that happens is that we load the graphics module into RAM. Then here we temporarily we save the registers of the VTC 80-column chip into an array in memory. Then we set the VTC up for 16 by 25 and set all the settings for the VTC. And it's a pretty long little loop. And we clear the big screen again. We clear all the VTC attributes on all the VTC screen memory. We disable the function key macros by default on the 128. If you press F1, it will actually output a macro. So if you press F3, it will output the monitor command and so on. We disable that here because we want to use the keys as actual function keys, not as macro keys. And, here we load the graphical assets into memory. So this is where the graphics and the map and so on are loaded into memory, and the font as well. And we zero the user action variables, and we return back to the main. Right below the init function is the exit function, which basically returns back to the 1 MHz mode at one point in the init code. The main code somewhere, where is it? Somewhere slightly lower, we switch to the 2 MHz mode. When we exit, we return that, and we restore registers and so on. Restore the RAM configuration register and the MMU control register. So you basically return to a functioning C128, but the code is all gone because it's been replaced by ROM basically. So if you want to load the game again, you will just have to load the entire game back. Then we print on the VIC2 screen. This is basically the message for the user to switch to the 80-column mode. We're printing this on the 40-column screen, and this is our last chance to do that, because when we switch to 2 MHz mode on the actual 128, the VIC screen gets garbled. It does work in WISE, but it doesn't actually work on the hardware. And we draw the various windows for the game, and we draw the megahertz text, which is basically telling the user we're about to switch it into 2 MHz mode. And we wait for a key press, and then we switch to 2 MHz mode. Once the user has accepted that we're going to do this, this is where it jumps into the SID player. That's the next thing that happens after you go to 2 MHz mode. And we take a quick gander at the SID player. It's here somewhere. What it does here is it disables the interrupts, because we can't be interrupted while we're doing this. Then there's a jump vector here at address 314 and 315 in hex, which sets, which is the jump vector that the 128 uses when it's going into the interrupt handling routine. So whenever it runs the interrupt code, it will jump into this address, find whichever memory address is here, and automatically jump into that piece of memory. So the address that we put here is basically our little player, the IRQ player. So we load the address of the IRQ player here, the lower and the upper part of the address, into the jump vector, and then we set some defaults, and there are some things that we need to do here. We need to set the raster interrupts of the pic and so on to init the music code. This code isn't terribly complicated. It's from Codebase 64, and it's largely unmodified here. What has been slightly modified here is the IRQ code, and the last thing we do after we leave this is we re-enable the interrupts and return. This is the actual code that's run by the interrupt routine itself, and this is called basically by the interrupt code itself in the kernel. And what it needs to do is needs to start up, and then it needs to jump directly to the song, and then it needs to basically jump to two separate subroutines. One of them is at C22C. That's basically the rest of the interrupt handling routine that's generally located here, because we've done a little bit of this. We've made it jump into the sit routine and made it play the song, and we've acknowledged any vector interrupts that have happened in the meantime for the raster. But we haven't really done anything else, so the rest of the interrupt routine still needs to run. So that's what happens here. We jump into it after it's done a little bit, and then we jump into the rest of the IRQ handling routine after we're done with this, to have it finish it up and return to the code. So in this way, it although we've replaced the routine, we're only basically just replacing the top of the routine, and then we're just dumping into the regular system routine and having it finish what it usually does and return back to the code. This seems to work absolutely fine. The music plays fine and at the right speed, and all of the other code seems to work fine as well. So this largely seems to work, which is good. Now if we go back to the main, once it started the sit player, which will start the music, it draws the greeting text that you see at the start of the game, and then it preps the game view, clears the VIC2 screen finally. Other than the debug, nothing else is ever shown on the 40 column screen. And then obviously I need some way of fixing the user in space. So right now this is just static. The user starts at 7-9 facing north. We take a look at the map again. That's basically forget where exactly it's here. Oh, 7-5 facing north. Yeah, didn't really make sense either. Makes far more sense. Basically here, so we're in this square, on the inside, sitting in this square. And then we just statically configure the sky and the ground color. This is something that will eventually, all of this is something that will eventually be loaded into the game and saved into the game. When we save the game, we will save the position and part of the map that is loaded. Will also contain whatever sky and ground color that you will use, and probably the graphics for the sky and ground as well. Right now they're just blocks of color, and they will be something else. And we're statically configuring the color of the sides and so on here as well. And then we just call the draw game routine, which we'll take a look at in a bit. That basically draws the 3D view. And then there's the forever loop. And all that really does is wait for key input. And as you can see here, we're allowing both the keypad and the cursor forward, left, right, backwards, and so on. We allow the X key to be pressed so we can exit, and then we just jump back to the forever loop if nothing else happens. So the only way to exit this loop is basically through the exit routine. If you press the X, and then there's the comparison routine, which just sets whatever it is that the user wants to do and stores it into the user action variable. Then it draws the game, and the draw game routine will load the user action, figure out what it is that the user wants to do, and move him accordingly. And then it will just move back to the forever loop. And there's the exit loop, which is pretty simple. It just makes sure that the user actually wanted to quit, asks for a yes and no. If you get a no, we jump back to forever. If we get a yes, we go back. We go to leave, which calls the exit routine and exits the program. That's basically the main routine. Obviously, more things need to be added here. There are other actions that we need to do, load and save and so on, and different actions for combat and so on. There's lots of things that need to be added here, but essentially this is the main game loop. For the graphics routines, the draw game routine is by far the most complicated in the game so far. It's also by far the longest one. We just go through it a little bit. That loads the user action, which we already know how was set, based on basically on what key the user pressed. And if it's set to 0, which it is at the start, it will just draw whatever position we're actually in. So it will not move anything. If it's not 0, we will call this move party routine. That's actually part of the utility package. And that also calls the user action. It checks what it is that the user actually wants to do. If the user is moving forward, then we call the move party forward routine and jump to the end of the routine because we've already moved the user. If it's not forward, and we check whether it's backwards. If it is, we move the party backwards, jump to the end of the routine. If it's then we check whether it's left. If the user is turning left, we also need the direction, so we load the party direction here, and we bit compare it with the wall comparison constant. I'll show you this in a bit. Where are the constants? This is basically a bit value, which is checking for bits 6, 7, and 1. And the way this is set up now, we're using bits 1, 6, and 7 for the direction, and also for checking whether the wall is solid or not. We're using this. There are 4 possible values that can be set, and we're using all of them within this bit comparison. And this is a very quick and dirty way to check all of these bits at the same time, which does save a bit of both resources and time. So what happens here, it will check the party direction, which is obviously north, east, south, or west. And the values are set to bit 7 is set if you're facing north, bit 6 is set if you're facing east, bit 1 is set if you're facing south, and it's all 0 if you're facing west. So if bit 7 was set, then the result of the bit is that the negative flag will have been set in the CPU, and that means we're currently facing north. So then we jump to the left north. If we haven't moved here, then it means that bit 7 is not set, so we're not facing north. And if that is the case, then things are simpler, because there is a side track if we're actually facing north, because that means that we have to do something different. If we're not facing north, if we're facing any other direction than north, we can simply... Hey there, Amiga Turn the Gamer, welcome in. We can just reduce the height by 1. And, let me explain why that works. Because if we take a look back into the 40 column screen, how do you like my sit? Since you're here, I can show you the game. We have a maze. We can draw a maze. We can move within the maze. We go inside the maze, turn around. Go into the box in the middle, leave the maze. A bit. It's by accident though, it's not really owned by design. I just need some way of populating these. This drawing code is largely done. What I wanted to show right now is that why this would work. If we jump into the, I'm facing north right now, where essentially we're here. This is the square we're on. Let's see, where's the... We're here. This is where we are. This square in front of what is essentially this door. So we're facing north, we're facing this door over here. And as we can see by the debug code on the 40 column screen, we're in X7Y4 facing north. And that means that the height byte is 0. But if we turn, so the value of the map for north is the high byte is A0, the low byte is 47. And it's A0 because we're facing north at the moment. If I go to the 80 column screen and I turn us east, and it's A147. If I turn us again to south, it's A247, and if I turn us to the west, it's A347. Now, obviously, if we want to turn left, which is essentially west, and we're already facing west, then what do we need to do? It's A347 now, and if we want to move left, it needs to become A247. The same is true if we're facing south. If we want to move left from south, it will become A147, and the same is true if we're facing east. We're going to turn north, it will become A047. So for the case of facing west, south, and east, all we need to do is reduce this value by 1. That is not true if we're facing north, however, because if we turn left now, we need to add 3 instead of reducing 1, because we're basically wrapping over. So that's the reason there is a special case. That's the reason there is a special case in the code here for when we're facing north. Otherwise, we just need to basically reduce it by 1 and store it back into the array. Then we have a separate branch here for the east and south. And, if we haven't branched when we reach this, we should have branched here if we're facing north. We should have branched here if we're facing either east or south. And if we haven't branched, we're obviously facing west. So we can just turn the direction to south and store that in the party direction, because chasing the array is one thing. We also need to store the actual direction we're facing into the party direction as well, since that changed obviously. That's basically what left east does. If we were east and we turned left or west, we're facing north. If we were south and we turned west, we're now facing east. Then there's the special case here for the north, where we need to add 3 instead of reduce 1. And if we were north and we turn to the west, we're now facing west, and we need to store that into the party direction. And after each of these is done, we jump into the moved. Then there's the corner case of where the user is. We already checked whether the user was moving forward or backwards. He's not moving forward or backwards. We already checked whether the user is moving left. He's not moving left, so all that remains is that he has to be moving right then, otherwise we wouldn't be here. So we have basically the same, except here the odd case out is the west direction, for exactly the same reason as we had before. We take another gander at the code again. The game again, I meant to say. We're facing west. And we take a look at this. And now at A347. So if we want to move east from here, we need to reduce it by 3, because it needs to become A047. We're now going to be facing north now instead of west. But in every other case, we just need to add 1. So the odd case out here is the west direction. Then we need to add 3 or reduce it by 3. Otherwise, we just need to add 1 instead of subtract 1 for the movement to the west. this code is essentially the same, except it's now adding one instead of reducing it by one, and then it's obviously doing the same thing for the direction. And here's the corner case for when we're actually facing west, where we need to subtract it by 3 to make it a 0 again. And then there's the various cases of changing that direction. Then we go here after we've moved the user. Right now there's this debug, which basically just prints whatever direction the user is facing, and prints all of the information about where the user is, etc. on the big screen. And then we just, I have a lot of debugging code in this routine right now, because it's very useful for the drawing routine to have all this debug in place. Because you need to be able to, it was very useful when I was using the drawing code to be able to figure this out. Actually moving the user around is the easiest thing. Drawing all of this is by far more complicated. So after we've moved the party, if we need to move the party, if we are just starting at 0, then we basically prep the game view, and all that does is draw the sky and the ground, and it's best to do that before we start drawing any walls and so on into the space. It reduces the flicker on screen, and it reduces the color clashing. And then we set the starting position. This is basically the start of the game view itself, which is at X position 2, Y position 1. It's essentially at the start here, at the a very early part of the right where the window starts. And then we call this little routine called find array location, and all that does is it's a little helper routine that we can call. It loads the party's Y position into the accumulator, and it shifts it 4 times and places it into the higher nibble. So if the Y position was 7, and it was then 0, 7, it's now 7, 0 instead of 0, 7, because we moved the 7 from the lower nibble into the higher one. We swapped seeds essentially, and then we take the X position, which we decided is 4, and we OR that value in. So essentially, if probably easiest to understand this in binary. If the Y was 7, that's 0, 1, 1, 1. And if the X is 4, that's 0, 1, 0, 0, right? So we take the Y position first, which would look like this. We shift it 4 times, so it ends up like this. We shift it left 4 times. So 1 shifted once, twice, 3 times, 4 times, ends up here. This one ends up here. This one ends up here. These values all become 0. Then we take this and we OR it with what is essentially this. Every bit that is 1 becomes 1. Every bit that has 0 in both values becomes 0. This one is 0, 1, 1, 1, 0, 1, 0, 0. So now it has changed from being 0, 7 and 0, 4 into being 74. This is 7, this is 4. This is a very nice way to store, but it's essentially the low byte of the user position. So we can access the array, the map array itself. So if we take a look at the debug again, you can see that A047. So the Y position is at the front, and then you have the X position at the back. And the A0 means we're facing north, so it's A040. The user is facing north and is at location 47 or 74, depending on how you look at it. Because the Y value needs to be before the rows need to be before the columns for the array to make sense. So they're effectively reversed. The Y value is first in the array, the X value is later. Now we need to bit the party's direction, and we already sort of went through this. F0, which is just a 7-bit set, means we're facing north. 6-bit set means we're facing east. The first bit set means we're facing north, and if it's all 0, we're facing west. So we load the comparison in and we bit it with the direction. Then we branch on the different possible values. It's north, east or south, or if it's not north, east or south, it has to be west, right? And if the user is facing west, we already know what the height byte is, because it's always A3. If he's facing north, we know the height byte is A0. If he's facing east, it's A1, and if he's facing south, it's A2. And once we've set this, we jump into this part, which means we've already set the array. We know what the low and high byte of the array is. We know where the user is located. And then we just load the value in memory for this particular placement in the array. This is basically loading the map value, depending on which direction the user is facing, into this map value variable. So we know whether the wall is a solid or not. And essentially also know whether it's a door or a fake wall or whatever it is. There are 4 different values. And it can basically be a solid wall, which is with bit 7 set. It can be a door, which has bit 6 set. It can be a fake wall, which essentially means it's a wall, but it's not actually solid, so you could walk through it. Or it can be empty, which means that it's 0. These are basically, the solid is bit 7, the door is bit 6, the fake wall is bit 1, and if everything is 0, it's empty. It's basically using exactly the same values as the direction. Then that's just a bit of debugging here, where it's actually printing that the array is set, and this is actually what prints that out on the VIC-40 screen, and then it returns. So once we've called this routine, the array has been set and the variable values have been set. Now the drawing code starts. And, what we do here is we change the direction to the west, and that basically goes through all of this and essentially in memory moves the user west. It doesn't actually move the party anywhere, but it turns the party west so we can draw whatever is west of the party. And then starts the code. What exactly it is about drawing. Is this a solid wall that is there? If it is, we need to draw a side since it's to the west of us. You can see this if we take a look at the actual display again. We move a little bit. We move into the square in the middle. Hey there, Josh. Welcome in. I'm slowly going through the drawing code. I was just showing this off. We're in this little maze here. We can go in and out and jump through things and turn and do stuff. it's moved on a bit. And we have SID music. It's not the best SID music in the world, because I wrote it, but it's still SID music. It's enough to get us moving at least. Amiga Gamer hasn't gotten over the witch still. Maybe you can incorporate the witch into this game, Amiga Gamer. Not entirely without. It's within our realms at least. We could easily do that. But, I'm fairly happy with how fast this routine is. It's plenty fast enough to actually use the game. Doesn't lag at all, even if you run pretty fast through it. So that's decently nice, even though it's quite complicated. I was just starting to explain the intricacies of the actual drawing of this, all of this stuff. And it needs to draw the sides, and I was going to show off the sides. That's why I went there in the first place. We go here. You can see the solid red pieces on the west and east side of us if we're facing north right now. So this is a solid wall to the north, and then you have two sides on the left and right. On the west and east side, basically. That means there's a solid wall to the west and east of us. Right now, it's always draws a solid. It doesn't care if it's a solid, a door, or a fake wall. It always draws the same block, but at some point you'll have to do something about the door, because you have to indicate there's an actual door. It's not just a solid wall, but that's not the most complicated code in the world. I haven't fully decided what I will actually do with the door. One option is to draw it exactly like the solid, and then just have a variable that describes whether there's a door or not. If the door variable is 1, we will add the door after we've drawn the solid wall. That seems like the simplest possible solution, because that means that I don't have to complicate the side drawing code more than it already is. The other potential solution is to make a separate routine that draws the door. So after we've done drawing the side, we'll check if there's an actual door, and if there is a door, we draw the door, because basically what this code does right now is it just checks whether it's a 0. If it's a 0, there's nothing there, and we don't need to draw the side. If there is something there, we do need to draw a solid side. It doesn't matter whether it's a solid wall or a fake wall or a door. There always needs to be a side. The question is more whether what else it is that we need to do. So in the case of a door, we either need to add that code to the subroutine that draws the side wall, or we need to add a separated routine and a separate function here which checks the value and then makes some sort of door. We need to draw the door somehow. What we do then is now we've changed the party direction westward. Now we do the same. We change the party direction eastward. We haven't actually moved the party anywhere. We're just moving blocks around in memory, and then we basically do the same thing for the right side as we did for the left one. If we're actually there's a lot of code now, a lot of conditional code that checks whether we're actually done or not. Because at some point when you're doing a drawing like this, like in this particular instance, if we've already drawn what is essentially the largest possible side piece to the west or east, there's nothing more to draw. The user can't see anything else, so there's no point of going through further drawing routines at this point, because we don't need to draw anything more to the left of the user. We don't need to draw anything more to the right of the user either. He won't be able to see it anyway, so it's a waste of resources to do so. So when we're done drawing something, we will store the value 1 into right done, and we will store the value 1 into left done. If we're not done, then we will possibly check further east and west of the user whether there's something else that we need to draw so that the user gets a better idea of where he's actually located. For example, if we go back here, there's obviously no side, and if we go here, then obviously there's nothing directly to the west of us, but there is something to the west and forward, so we need to draw a semblance of a wall west and east facing forward. The same is true here, and it's true here as well. We need to tell the user there's nothing here, 2 squares west, basically there's nothing here, 2 squares east, but there is a solid wall, 1 to the east, 2 forward, and there's a solid wall, 1 to the west and 2 forward. There's a solid wall, basically 1 square to the north. We need to somehow draw all of this while also maintaining some sort of for example, if we go back 1 now, it will just draw 4 squares ahead max. It will not draw anything that's further away than this, because essentially that would get lost anyway, and it just makes the drawing code even more complicated than it is now. It's plenty complicated enough. And then there are various variables here that just check whether we're actually done with the left and right side, and if we're not done, then we check more things. Is there something hey, they're raising the beam, welcome in. Yeah, I'm decently happy with this. We check whether there's something to the east and then forward, and so on. And then we now check whatever is directly in front of the user, and if there's something directly in front of the user, we draw the wall, and then we store center done, because if there's a wall directly in front of the user, we're not going to be drawing anything after that, and we don't need to worry about drawing any other walls. If we're standing directly in front of a wall, like we are in this case, we've drawn the west, there's a solid wall. To the west and 1 forward, there's a solid wall to the east and 1 forward, and there's a solid wall in front of us. This is all we draw. If we now move back, it's essentially the same, except it's 1 square distant. If we move back forward, then now we're essentially drawing an empty here to the far east and far west, and essentially the same directly in front of us, and 1 square to the west and east. And, for example, where we're in here, this is perhaps the simplest case. There's a solid wall on the west, there's a solid wall on the east, and there's a wall directly in front of us. That's all we draw. Don't need to draw anything else. And, just for reference again, for raising the beam, we're inside this little maze here. This is the map maker. We were inside this little square here in the middle, where it's basically just lots of solid walls. And then the code moves forward. Well, this is essentially the map maker. It's a little Python program that I wrote, and it just creates the arrays that we need for the game, so we can actually have the map drawn. And there are different. You can basically click any square and set whatever is there. Right now, this is the game right now doesn't care whether it's a solid or a door or a fake wall. It's just either empty or it's not empty. And if it's not empty, then it draws a solid, and it doesn't actually check whether something is solid or not. You can walk through everything right now, and essentially you can. We've created this little maze here with 4 doors and a fake wall in the middle, and everything on the outside is basically just empty. And we can walk around this little map back and forth, and we can make any map we want, and we can save any map we want, basically. And this is just a tool to make the DAT file, but it's a very handy little tool. And we walk around the maze a bit. Here we're on the outside of the map. We can go around the edges on all of the sides. We can go inside. This is the little solid square that's in the middle. We can see all of the different endpoints. We can of course go out again. We can walk around in our little maze. It's an interactive 3D maze at the moment. That's what it is, with SID music. Interactive 3D maze with SID music. Better than nothing, I guess. Now, perhaps we never need to run any of this code, but this is where we start drawing code for something that is not directly in front of us and not directly to the west and east. And it essentially does the same thing, except the first thing that it does is it moves the memory array 1 square forward. So in memory it moves the actual location of the drawing 1 square forward, and then it essentially does the same as the code before. It checks on the west and east and directly in front whether there's something that we actually need to draw. And now we get to code where it's skipping a lot of code if it doesn't need to draw it. This is one example. There's already a center wall directly in front of us that we don't care whether the wall in front of that is solid or whether something in front of that to the west or east is solid or not, because the user won't see it anyway. We'll just skip it. The same is true here for the right side. And the same is true here for the centerpiece. So if we've already drawn something in the center, or we've already drawn something to the left and right, just skip all of this. Then we move forward again, and this is the third part of the routines, where we draw something that is basically 2 squares in front of us. And it's essentially the same. This is where the code starts getting a little bit annoying, because here it matters, for example, when you're drawing the wall that is not directly in front of the user but 1 square away perhaps. these took the longest time was spent on this nonsense. Because if you take a look at the drawing code here, this wall, there is basically one square forward and to the west. It won't look the same if we're going backwards. It can't be the same size either, so you have to have exceptions for that. And now it also matters whether there's something to the left or right of this as well. And you need to be somewhat careful of making the colors match up again as well, so you don't end up for example here I've tried in many cases to have it doesn't always fit, but I've made attempts at making sure that the colors clash, so you can clearly see where one wall starts and another one ends. Eventually we will have to redo all of these graphics and do them better, but at the moment it's pretty clear where you actually are. This was a lot of work. Getting all of this to line up properly with all of the various corner cases there are was a lot of work. And then there's the last piece of the drawing code, which is basically just, it's 3 squares fully forward. That's as far as we draw. So once we've done that for all of the various different things that we could potentially have drawn already and that we could potentially have drawn, we're done and we can return back. Now this is only half the code, because all of the code that actually draws these different things is separated into separate routines. And, I'll just go through wall 4, which is the wall that is furthest away from us, and take you through the this is the most complicated bit of drawing, because it's potentially the one that has the most variance. So here there are 5 different potential types of the wall. There's the leftmost wall, which is just 2 tiny blocks, which give the illusion of a wall being basically at the far far west of the user. Then you have the wall directly west of the user. Then you have the wall that is straight in front of the user, but 4 squares away. Then you have the wall that is east of the user, and then you have the wall that is far east of the user. So essentially you have 5 different walls that you could be drawing with this function, depending on exactly what it is that the user is looking at and how much of this he can actually see. If he's standing far enough away and there's just empty space in the way, and there's a wall, solid long wall to the north of him, then he will see all of these bits of the wall. He will see all 5 of them essentially. So if we were to do something like we make this solid. Actually needs to be further away. Perhaps not the best example. That's an obvious bug. An interesting one, but an obvious bug. there. Doesn't matter. So let's assume we are actually standing in this square over here and looking forward. And you would see this would be the center wall, type 3. This would be type 2 and 4, either on the west and east side. And this would be type 1 and 5. So you would see this entire block here, if there's nothing in our way. If we add something directly in front of the user, you would only see a part of this, because a part of it would be blocked by the wall anyway. So the code needs to take all of that into consideration before calling the wall code, and it will already have decided which type of wall it is that the code needs to draw. So all this code needs to do is the actual drawing of the wall, which is still easier said than done, because we need to pick the colors, we need to pick the starting position of the wall, the height of the wall, and the width of the wall, and then we need to actually do the drawing part, right to the VTC and so on, repeat it, loop it. I've tried to do this in a way which saves as much CPU time and VTC time as is humanly possible, and it does an okay job. It's fast enough. You can see, however, that just this code that draws the wall here, all this code does is just draw wall 4. Still a lot of code. And, this is why the graphics subroutines are now by far the biggest part of the code. There's something like 10K now with all of the various different things. In theory, there's not a ton to add at this point. I don't see it ballooning way past 16K or anything like that. We might change the graphics and we might add some routines to draw the door and so on, but it's not going to add a significant amount of code to this. It's more of an addition. And we might be able to do the door drawing code with inside the site and wall drawing code as well, to save a little bit of space. I'm all for trying to split this into as many different subroutines as you can, though, because they're already quite complicated, and even if I've commented them very well, it can still end up being very annoying to debug. So I would rather waste a little bit of memory if I can than having to do a lot of conditionals inside the code. It's easier if you don't have to. We'll see what restraints we have to follow. Now we've essentially done this, and we're decently happy with it, and it's been slightly debugged. It's obviously alpha still, and there are obviously and almost assuredly some bugs in this still. We can start working on the game mechanics itself, and more things that we need to do with the graphics. One thing I've already considered and that I'm working on is another tool. It's basically the last thing I did before I went to Omega 37 in Germany. Let's see, where's the... this. Is the sit song growing on you, or do we want to kill it? It is very repetitive. But it's just something I whipped up. I whipped up a few Go Tracker tunes, a few sub-tunes to have some music, to get the music integrated into the game as well. Let's see. What I want to to show you now is the pic-maker. Some modules in here. Let's see. I'm developing all of this on 2 different machines. I'm both developing it on the Windows machine and the Mac. On the Windows machine, I'm using a Windows subsystem from Linux, and some of it is actually the Python stuff is running on the Windows side as well. So I need to keep all the modules synced between 3 different operating systems. Sometimes it is a bit of a pain in the ass, must be said. I think I can actually show this now. It's very wide. I need to squish it a bit so you can actually see it. You can't see, for some reason it doesn't capture the menu, but that doesn't really matter. The menu doesn't really have a lot. Essentially it just allows us to load in a graphic. This is something that I just took from the internet. It's not something that I will actually use as an asset in the game. It's just an example I took from the internet, sort of show you what it does. And I made this thing because the VTC obviously has limitations as to what they can do. It can do up to 2 colors, but the 2 colors have to be on an 8 by 8 block, essentially. On a character block, essentially, because each character block can basically have a separated foreground and background color. So you can have 2 colors on an 8 by 8 block, but that's the limitation. You can't have more than 2 colors on the same 8 by 8 block. The next 8 by 8 block can have a different foreground and background color, and it won't clash, but each block needs to be on an 8 by 8. So there are definite limits as to what you can actually do with the graphic. And one of the things is also that you have a fixed palette, so you can't just pick any palette. It's a fixed palette of a few colors, which you can't change at all. Somewhat well known. I think I have them here somewhere. Yeah, they're here. These are essentially the colors that we can choose. These are the it's missing white, but the 16 colors that are available are basically these 15, and then white, fully black, fully white, and these 14 different colors. This is it. And obviously one of the first things that we need to do somehow is map things to the palette. That's one thing. And then we need to map it so that we're not using more than 2 colors on an 8 by 8 block, so we can actually display it. That's another thing. So what this little tool does is it takes the picture that you load in, and can't actually see all of it. Now you can see all of it. First, the middle is basically after reducing the palette. First, of course, we need to scale it down because this is a big picture that we loaded from the internet. So we start by scaling it down to fixed width. And look up if we take a quick gander into code for this. This is the pic-maker written in Python. I'm trying to remember how much I reduced the size here. There is definitely a size limit that is done. We resize it here so we can display it on the GUI itself, but that's not actually what. This is the color reduction code. We'll take a look at that in a bit. Yeah, so it's 200 pixels white max. We do whatever we got in, but we resize it to 200 white. That's the first pass. That's just taking it, mapping it down to 200 pixels white, and then reducing it to the VTC palette. And if you could basically display every single color on every single pixel, we could have it look like this. This is basically after the first reduction. Obviously it doesn't look exactly like the source image because we've severely reduced the number of colors we can actually choose. And based on the palette that we saw earlier, we don't actually have a ton of choices for the different colors. We obviously have the black and we have the gray we can use, and then we have the 2 shades of the red, and then we have a brown shade, and that's basically what it's mapped to. This is a decently good conversion of this, essentially the source, into the limitations that we have with the VTC. So this is decently close to what we had on the other end, and the third one is then also bound by the limitations of having to have just 2 colors on an 8x8 block. So it's been even further reduced, and you can sort of see what it would look like if we were to display it on the VTC screen itself. It would obviously look slightly better because it's a lower resolution, but still there are limits. I wrote this tool essentially so we could load assets in and convert them pretty easily to have them displayed on the VTC. There's a decent chance I won't do any of the scaling work because sort of depends. I might scale the assets before I take them in. I'll have to give it some thought. But it's mostly the palette reduction and following the limitations of the 8x8 that is important here, because we want to have graphics for you probably want to have at least one graphic for every monster type or whatever that we show on the screen when you're battling the monster. It will be something like if you're fighting whichever monster starts the fight at the front will get its picture displayed in the game view while you're actually fighting it. So we will want to have that a decently large graphic, and we obviously need some assets for that, and we need some way to map it so it actually looks decent on screen. And the point of this Python program is then to be able to write the ready image in a file format and that is suited for display, so we can basically write it into a DAT that is very easy to write a routine to just dump it directly on the screen. So there's as little code that needs to be done in the game itself as possible, and the tool does 99% of the work of taking the asset picture in, color reducing it, and then reducing it to the 8x8 limit. So you can write it directly into a file, and then incorporate that file directly into some sort of block of graphics that we can import into the game. So the tool itself is largely ready. It uses bits and pieces from various other things, but I also wrote part of it myself because I wasn't completely happy with some of it. So if you take a look at the main code, it's simple enough. We're still using this what's it called again? It's called GUI 0, a simple GUI environment for Python, which is essentially built on top of TK, which I'm also using in this to draw directly to the canvas somewhat. It's just a simple menu bar with some load, save options and about option and so on. Then we have this single render button, which just takes whatever source is already in there and converts it in 2 steps. Then we have 3 canvas pieces, one for the original source, one for one pass, and the second one for the second pass. That will become more clear as we go on. And the load file, what that essentially does is just read it into an image object. And it does size reduce it for display, but it doesn't actually size reduce it for working with the actual image. And then it displays it directly into the canvas window in the GUI, so you can see it after you load it. And the save is simple enough, just takes the resulting image and saves it to a file. I will work on this to make it essentially save just an array. We can incorporate into the game. Right now it just saves the raw image directly to disk. And then there's the color reduce routine. This is really where a magic happens. I already have the VTC palette itself. Find here near the top as RGB values, and in the right order as well. Color 0 is at 0 and so on. So the last color is white, the first color is black, and then you have the various different shades of the VTC saved into different values. That's essentially what it uses. And then it's using a distance, and the distance in this sense is how far the current color of the source image is from the color that we are currently looping through with the palette. And we loop here and we calculate what is known as the perceptual color distance of the color. And this is basically quantization. And we end up with what is, after going through all the loops, we end up with what is essentially the closest color in the VTC palette to whatever color is actually in the source image. And so this is basically pass 1. All it does is map whatever image we have to the limited palette that we actually get to play with, so that we choose the closest possible color for each available picture in the image. That's pass 1. And once we've gone through it once and selected once we've done the closest color and set the closest possible color that we have for each and every pixel, we have essentially the image that is put into the middle, which is after pass 1. What we do now, after we've done this, is we create a little array, and we go through each and every 8x8 block, and we find the 2 colors that are most used in that particular 8x8 block. So essentially what we want to do is we have a foreground and a background color, and we want to find the 2 colors that would best represent the current 8x8 block. So we go through each of the 8x8 pixels, and we select whichever 2 colors are mostly used. This is crude, but it's sort of what we have to do. And once we've done this, we now make a very small palette which just contains the 2 colors that are mostly used. So if we go through an 8x8 block, that is essentially the tail over here, for example. And obviously we need to we can see sort of that gray and black are the predominant colors here, and there are more gray and black pixels than there are of any other color. So that's essentially what gets picked on the other side. Just, we can't really do any more colors, we can only do 2 of them. And if we're going to do 2 colors out of this 8x8 block, then it has to be gray and black, because those are the most used in the block. So those are the ones that get picked. And that also means that any pixel that is in this 8x8 block has to be either gray or black. Can't be any other color than gray or black. This also means that often you end up, for example, with the tail and some of the features on the ends, you end up in a situation where the most common color is perhaps just white, and you might end up with a block that is largely just white, because none of the other colors are actually close enough match. And then we take this 2 color palette, and we basically go through the picture on an 8x8 grid again, and we pick whether the color is closer to being the first color, which is then the foreground color, or the second color, which is the background color. That's essentially what is in pass 2, which is the finished image that we could display on the VTC. And essentially when we write the array, the foreground color will be 1 value, which will be just 0, and the background will be the other way around, because essentially the way it works in VTC memory, this is just monochrome. It's an on and off thing, but it has different colors. So you can set the foreground and the background, but essentially it is monochrome. It is only really 2 colors. It's either set or not. So it's either 0 or 1. That's the way it has to be saved. And obviously there are limits as to what we can do with this. And some of the demos that are using the VTC, they do some interesting tricks. One of them is reducing the size of the card block into an 8x1 block, but that also means that you have to use 8 times more memory, because essentially you need a lot more attribute memory, and then you also need a lot more pixel memory. So we can't really do that, and there is also pokery required to actually do it as well. So we'll stick to the limitations that we have, and try to make sure that the assets that we end up using are made in such a way that they will actually look semi-decent on screen. They probably won't be perfect. I'm not an artist, and I need to find some way of incorporating assets from somebody else into the game, and I will have to use some tool like this to do it, because it would probably be best, and we would get the best outcome if the artist drew a completely new set of art based on the limitations of the VTC chip using the palette that we already have and know with the limitations in place, and then you could probably make it look so that the limitations aren't there. But if we're going to be using external assets, there's always going to be some sort of trade-off, and some assets will probably look better than others, and I will just have to go through a decent set of them and try to find something that looks semi-decent. That's really the best I can do, unless you want to volunteer to draw art for the game. That's what we'll end up with. I need some sort of tool to do this, and I've already written that tool and I'm decently happy with it, so we'll go ahead with that. Next on the agenda really is the game itself. Need to start making a map of the first town. I need to the tools are in Python. The game itself is in 6502 assembly because it's on the 128. Have you actually seen the game, amigo? I want to. Did you just arrive? Welcome in, by the way. Let me switch. This is the 40 column chip, which is essentially the C64. And this is the 80 column chip, which is the 128. Jump back into Wise here. This is essentially the game. It's running around in this little map that we've made with another tool. You can run around this little maze, turning in all directions and seeing what it looks like, and walk back and forth and so on. Right now it's an interactive. It's an interactive map viewer with SID music. But the eventual plan is to try to make it a role-playing game. The 80 column chip is very limited as to what they can actually do. Essentially it's meant for text display. And the history behind it is that before Commodore acquired the Amiga, they were actively developing something called the Commodore 900, which was supposed to be a Unix workstation. And they were largely done with it, and funnily enough, the Commodore 900 case looks quite a bit like the Amiga 2000 case that ended up coming from Germany, which was essentially the same development unit. And one of the chips that they had already designed to put into that machine was this the frame buffer text display chip, which is the VTC, and it has its own dedicated memory. And by default on the 128 it has 16K of dedicated memory. It has its own video memory, and it can draw text, and it has bitmap mode that we're actually using, but there are limitations as to what they can actually do. It has to work in 8x8 blocks. That's one of the reasons the pic-maker tool works like this, because this is just a dummy picture I took from the internet. It's not something I plan to use in the game. It's just it's a good example of how the tool works, because it's a higher resolution 24-bit image. The first task is to reduce the palette so it actually matches the VTC palette, which is just a fixed 16 color palette which can't be changed. It's essentially the same as or pretty close to being the same as a. See if I can find a better picture of it here. It's essentially very similar to the CGA palette, but it has slightly more colors in it. It's an RGB it's a digital RGB 15 kilohertz signal that comes out of the port on the back. If I switch back here, this is essentially the palette itself. It's 16 different colors, 2 shades of blue, green, and cyan. 2 shades of what is essentially red. It's not quite red, but it's close to being red. 2 shades of purple, a brown, a yellow. It has the 2 different shades of grey, and it has the white and black. That's it. So everything that you draw needs to have, yeah, it does look very similar to, it's quite similar to the CGI, except that with CGI you have more limitations. You can only basically have 4 colors on screen at once, but you can change, you have a few different palettes that you can choose from. So you can have the yellow and red together, you can have the cyan and magenta together. I don't remember exactly how it is, but it's essentially the same palette, but you can use any of these colors on screen. You're not limited to using only 4 of them. But it's very close to being the same thing. And the limitation, however, here is that although you can use any of the 16 colors, you can only use 2 colors on an 8x8 block, because essentially it's just, even the bitmap mode, it's essentially just a text display thing. So since the characters are 8x8, you can only select the foreground and background for every 8x8 character. So you have to make sure that you're not using more than 2 colors on a per 8x8. So that's basically what the first pass here on the image, it reduces it to match the palette that we're working with. It takes the closest color from the VTC palette based on the 24-bit palette that we're using and maps it together. The second pass makes sure that we're not using more than 2 colors on an 8x8. And this is just a way to be able to map some sort of graphical assets into the game and display them directly on screen, following the limitations that we actually have. Essentially, it's a monochrome display, but it's monochrome per 8x8. And the way the game is set up at the moment is that this is decently high resolution. It's 60 columns by 25 lines. So it's essentially 480 by 200 or so, 480 by 240. So it's decently high resolution, but bound by the limitations that we have. And of the 16K of the display memory, we're using 13.5 for the pixels, 1.5K for the color attributes, leaving about a K that we can use for storing assets directly in the VTC RAM. So we're pushing it with the memory that we have, and there's no way of double buffering, which is why we get a little bit of there's a slight sort of, as you can see, the flicker sometimes when it needs to change the, for example here, it needs to change the color on the back. You can see it sort of flickering before it can be done. That's because we can't double buffer it. So it's drawing on the screen while it's changing the color on the screen before we can swap it. If we had more default memory, we could essentially have another place in memory where we're actually drawing to it, and once we're done drawing, we could just swap the display pointer, which is essentially what double buffering does, but we don't have the memory to do so. It's somewhat similar to the EGA palette as well, but the EGA palette is slightly extended. You have 64 colors, and they're all basically the same, but different shades of the same 16 colors, but it's slightly more variant than this. This is somewhere between CGA and EGA. there is a way to expand the VTC memory. You can expand it on the 128 up to a full 64K, and on the original Commodore 900 workstation, I think it had way more screen memory. I think it had up to 128K, even more. So the chip can actually access more memory, and it's very interesting that it has its own memory, because that also means that the game is running in the Commodore 128 2 MHz mode, because although the VIC chip on the 128 is limited and can't really run in the 2 MHz mode, the VTC chip is not. So you can run the CPU at full speed and have the graphic chip work just fine nonetheless. So that means that the game can run slightly faster. We can do more things in the code while actively using 80-column graphics, and then it's just a matter of trying to make it look decent. The 128 is a very fascinating machine. It has 2 CPUs, it has 2 video chips, and you can essentially run all of them at the same time. So even since I'm developing this with Wise, and Wise doesn't actually have the limitation of not being able to use the VIC chip in 2 MHz mode, we can also use the VIC display. And I'm using the 40-column display for debug. Basically, it shows you where the user is on the screen. It updates as you run around. So if I actively run through the maze, you can see the values of the arrays changing on the 40-column screen. And there's at least one VIC-2 or C128 game that I know of that is actually using both displays. It uses both of the displays for the game at the same time, but that limits you to running the game at 1 MHz. Then you could essentially use the VIC display like you could use the C64 display and have access to the sprites and so on. And then you could use the 80-column display for something else, and you could run both of them at the same time and have a dual monitor game on the 128. So that's actually something you can do. So 128 is essentially 2 machines. It's the C64 as it is, with all the same stuff in it, and then it's a totally separated computer with a separate video display. And then it's essentially the third machine as well, since it also has a C80 processor, so you can actually, technically, you could run the code as C80 as well with the VTC display. So that's something that we might take a look at some point, whether that actually works or not. And, the game itself is written in 6502. I roughly went over how it works earlier. And, there's a lot of code, particularly the drawing code is at this point is perhaps by far the most complicated, because drawing this Pseudo 3D view is pretty complicated. Even if it only draws 4 squares forward, essentially. It's this subroutine called draw game that basically just draws the display as is. And we've made it to this point. The next point is basically to there isn't code yet in the game, although the game knows based on the map. Close this and open. So many tools, so many windows. I switch back here. Okay, essentially correct. That's another tool, Python tool called the map maker. This is what allows us to draw the maze and save it into a format that the game understands. This is essentially the map we're running around in. We start here essentially when you go into the game. We're positioned right here. This is this little maze that we're running around in. Game has the concept of a door. It has the concept of a fake wall and a solid wall. But right now the game doesn't care whether the wall is either solid, and that means it's a solid or a door or a fake wall. It doesn't care what it is, or it's empty. That's all it checks for. The game doesn't check whether you're running through a wall or not. It doesn't care, so you can basically run through walls and go wherever you want. But essentially the next step is to the user has to have some way of knowing that there is an actual door. There's no code that does that right now, so we need to signify that somehow. We need to draw a decent map for level 1, and we need to start working on the role-playing parts, being able to create characters, being able to equip some weapons and armor and so on, being able to assign values to them, being able to save the party, being able to save the game, the position, the map, so on. There's lots to do, but this is a little project that we started, and it's at least a proof of concept at this point. I will continue onwards with it this winter. Keep going, see how far it takes us. I'm essentially recreating something that will probably end up being pretty close to, if we get forward with the game, is something that will role-playing wise be some sort of mix between Might and Magic and some sort of D&D game. And, I hope we get to a point where it's decently playable and at least fun to play, even though I'm fairly sure the graphics and sound won't be excellent. I was able to whip up a few decent sit tunes, and I can import assets from itch.io that I can buy and sort of try to make them look semi-decent on the VTC, but that's about where my limitations lie. I was able to get along with Code Tracker long enough to actually make a few tunes and some sub-tunes, but I'm not the best sit artist in the world either, so if someone wants to volunteer to write something for the game, I would happily accept it. And, I don't plan on selling this either. This will probably just end up being published as open source, so people can look at how dreadful the code is, perhaps learn something, and perhaps build upon it and so on. I don't really care what people do with it, as long as they don't sell it, but obviously I wouldn't be able to incorporate any assets from itch.io that require purchase into the open source, so you would have to, if I were to make it available on GitHub, you would basically have to either buy the assets yourself or supply some other assets for the game. If I were to sell the game, I could basically sell the game with the assets in it, but the code would still probably be open source. But, I can't give away other people's work, obviously, but I can make it easy for you to access the code and build upon it, and if you want to do something else with it and incorporate something else in it, that would be great. I mostly started this because there's a distinct lack of 80-column games for the 128. And the little there is often pretty basic. Yeah, I'm sure we can at some point find them. I've already written the routine to play the sit, so they can play any sit. All it requires is that it needs to be in a particular place in memory, but that's pretty much the only limitation. So we would be able to. We have about, I think it's 2 kilobytes or something, maybe 3 kilobytes of RAM that we can actually use for the sit. So it needs to be able to fit into that. And, preferably I would like something like similar to a Code Tracker format, where Code Tracker has this concept of a sub-tune where you can reuse the same instruments, but even you could even reuse the same patterns, but you're basically changing the tunes within. So it's basically a sub-song within the total tune, and it does save a lot of RAM by doing it that way. So that would be a good way to fit more tunes into the same memory space. Although my concept was that we could have 3 or 4 tunes basically, or even more tunes per map, because once you change the map, go out of the map, you can change, once you load in a new map, you can basically change the graphics, you can change the tune, and so on. You're not bound to having the same tune for everything. You could reload once you change it, so you can easily replace the music on a per map basis. the tools I've written are actually just to help me make it as simple as possible in the assembly code to do things. It's much simpler if I can. Yeah, it's and the memory management on this platform is also just highly complicated. It's obviously still it's an 8-bit system, obviously, and so we can only basically access 64K of RAM. And the way the system starts, almost all of that RAM is being used by the various ROMs that are in place. So when you start at 128, essentially what you have is you have 10K of free memory to basic. That's it. Everything else is occupied by ROM. And although you have 128K of physical memory in the machine, you can only address by default a very small percentage of it. So the first thing we do in the code is it's change the memory configuration. There are lots of different memory configurations that you can actually have. So we essentially take this, we turn off the basic ROM, both the low and high, and the user ROM as well, and we free up 32K of RAM here. We can use this space from 1300 up to 1 FFF. This is where the SID goes. What's below 1300 in the C64 space where you generally place the SID, this is actually space that's being used by variables that are used by the kernel and other interrupt routines. You can't really write it there. It needs to be at 1300. And you have a little bit of space here up until the basic RAM. And this is where the main code starts, basically. So you have a little bit of space here that we use for the main code and the utility code. Then we have this space from 4000 up to 8000, which is used for the graphic drawing routines. And then we have this space from 8000 and up to basically essentially C000, which is used by the assets, the graphics and the map and so on. And this space, we can bank this space. So we can essentially have a single 16K here, and we can have another 16K bank that we can switch back and forth. Essentially, we have 64K of addressable memory, but we need to keep this because the kernel ROM is here, and I'm using some of the kernel routines for loading and saving the various modules back and forth. I will use them to load and save the game. There are also utilities routines that we can directly use from the kernel. We're using the interrupt routines. And we also need this I/O space here because we need to be able to talk to the 80-column chip, which sits here. So we can't bank this out anyway. So these 16K here are essentially ROM and I/O space, and we can't move them away. So this is bankable. The 16K here are bankable. This is basically fixed. So the code can sit in the lower 30K, then 32K, then you have essentially 2 times 16K here, which you can bank, and then you have a fixed 16K area here. And one of the first things that the code does is set the memory configuration back and forth, so you can fit all of this into RAM. And yeah, by default, 128 basically you have almost no memory free. There is more memory free on the C64 because there's just a lot of ROM. The basic ROM is much bigger than it is on the C64. The basic is much more advanced. You have way more commands that you can actually execute from it. So it takes up quite a bit of space since you can do quite a lot with it. And the kernel is also extended. There are routines in the 128 kernel that aren't on the 128 and so on. So there's quite a bit of by default. There's quite a bit of you can actually do, and you can also see here on the common you can select how much of this is common and how much of this is bankable depending on somewhat on what you want to do. But since we have so much code running, we have the maximum amount of common memory, which means that we have the fixed 32K of code memory, and we just have the 16K then of the shared, and then we're stuck with this at the top. It's all fun and games. I've had a lot of fun dealing with this though, because limitations are fun. It's fun to play around with this and get around the various limitations that you have. And next time around, I will have something. I will have some sort of blue plan as to what it is that we're going to be doing going forward. I do try to spend a little bit of time on this, even if it's only half an hour a day or whatever. And I find that if I already have a mindset of what it is that I'm going to do, I can get quite a bit done in half an hour, maybe an hour if I have an hour to work on it. Get quite a bit done. And there is also the problem with if you're stuck inside assembly code for a very long time, you can very easily lose focus. I find that I can do more with a 1 hour session every night than perhaps I would get done in a 5 hour session in one night. So after being inside assembly code for 5 hours, your brain is sort of mush. It's easier to distract yourself and or move back a little bit and do something else for a while and then come back to it, because it's very easy to get stuck inside the code. You can't see the error and you've gone over it again and again. It's very often beneficial to just step back and do something else and then return to it. In more cases than one, you will actually just immediately find the logic error once you return to it, even though you've been staring at it for hours before and trying to see it. Once you step back and go back to it, you immediately see it. So yeah, it's funny how that works. It's just when you're stuck, it's usually best to just either focus on coding something else or in a different part of the program, or just start doing different language even, or work on the graphics or whatever. It isn't actually beneficial to just keep going over the same code again and again. You won't actually get anywhere. I will probably call this a night. Going now for 2.5 hours. So normal weekday here, it's 12:30 already. I'm not sure how many of you are actually there. I don't generally advertise these streams on Twitter. I just advertise them on the Discord, and I advertise them. Of course, if you're following and you have the notifications set up, you can see it there. But I don't generally. Yeah, that's a good idea as well. Just switch projects and go do something completely different. Your brain is still fine. It's just not in a mood to process whatever it is that you're doing. It's funny how that works. I wonder if someone is on. We might be interested in rating. Dr. Mookhouse is doing Agony for the Amiga. Is doing some sort of SMAP challenge. Why not? Why not? I'll set it up. Thanks for coming, guys and gals, and I'm back here at least Saturday with more Might and Magic. Maybe we'll squeeze a stream in on Friday, I doubt it though. Until then, you enjoy the rest of your night, the rest of your week. Sleep well. Join me for the raid if you can. A raid message. If you have the emotes, use them. If you don't, use the non-emote one. I bid you good night.